we are now looking at chapter 3, which is mathematical models. We will only consider section 3.2 in this chapter, and section 3.2 is about compartmental analysis, which is like something happening in a compartment. So we are looking at changes happening in a compartment. So what do we mean by that? Well, in the case of mixing model, which we are not going to study much, but I will just tell you why we call it under the compartmental analysis, because in mixing model we look at changes happening inside a tank when some solution is already there and some more is being poured. Maybe the quantity of the substance or the concentration of the substance which is in the solution being poured is different from the concentration in the tank, and then at the same time it could happen that some of the that mixture in the tank is flowing out of the tank. So that's why we consider the tank as a compartment. In the case of population, we can look at the population of bacteria, which is produced in a petri dish in a lab. So the petri dish can be considered as a compartment. If you are going to look at the population of some animal or some insects on an island or in a city or in a habitat, and also maybe the population of humans in a country. So the country, the island, the petri dish, these can be considered as compartments. So let P of t, so we are going to denote the population by P. You can use uppercase P or lowercase p, doesn't matter. So P of t be the population of bacteria that reproduce by single simple cell division. Okay, so we assume that the growth rate is proportional to the population present, which makes sense. As long as there is sufficient space and some ample food supply, the bacteria will keep on growing, and we can assume there will be no death, because we look at the population of bacteria for a shorter time, not like years or centuries. So we can assume that death rate is 0. And also note that because this will be an increasing function, so the rate must be positive. So we said dp by dt is equal to k times p, because remember we said that dp by dt, the rate is going to be proportional to the amount present, or dp by dt is proportional to p. That's how we say. But then we can change the proportionality sign to equal to sign by putting a constant in with the right side. So when we are given the initial condition that p of 0 is equal to some number p naught, then this is called the population growth model, and this is called the Malthusian model of population growth. And for human population though, we cannot assume that the death rate is 0, but we can assume that the death, if we assume that the death is being caused only by natural causes, then we can assume that K2 is the constant due to death rate, and the K1 is the constant for the birth rate. Then dp by dt will be equal to k1p minus k2p, which is equal to k1 minus k2p, and the model we will have is dp by dt is equal to kp, where p naught sub 0 is equal to p of 0 is equal to p naught. So we get the same thing again. Now let us try to solve this model equation, this differential equation. So when we solve it, we can do it by what is it called, in the separation of variables. So I move the p over here, down here under dp, and the right hand side is now kdt. So when we integrate, the left hand side will give us ln of absolute value of p, and the right hand side will give us k times t plus a c, and here I am going to take it as c1. Then we can now convert this logarithmic form into exponential form by writing p is equal to e to the whatever is on the right hand side, and then I can use the some property of exponents, that if you have a raised to the power m plus n, then that can be written as a to the m times a to the n. So by writing it that way, I get the right hand side is equal to e to the kt times e to the c1. Now e is a constant, c1 is a constant, so e to the c1 is a constant, so I'm going to give it a new name, c sub 2. So that our model now looks like p of t is equal to c sub 2 of kt. So this is how the model looks, but we can now apply the initial condition, p of 0 is equal to p naught, and by doing that we end up getting p of t is equal to p naught e to the kt. So when you are going to solve these type of equations, you are going to find the solution of these type of differential equations. You must start with either with this function here, this type of function, or you can start from the beginning and show all this work and get here. Or if I say show something like this, then you have to show me all the work I have shown here. If not, I don't mention that, then you can start with this formula. So in the same way as this exponential growth model, we have an exponential decay model for substances that become smaller in amount as time passes. And the most common place where we use the decay model is with the amount of radioactive substance. So it is observed that radioactive substance decay at the rate that is proportional to the amount of the substance present at that time. So since this is the amount is decreasing, so the rate must be negative. So we have dq by dt is equal to negative kq, where q of 0 is equal to q sub 0, which means the amount at time t is equal to 0, or initial amount. And we following the same technique as I showed up there, we get this equation. The difference between this one and the population growth model is that we have a negative sign here, but in the growth model we have a positive sign there. Now the next type of model is the logistic model for population growth, and you can read this. Now the difference with this model from the previous is that in the Malthusian model we only consider the deaths by natural causes, but in human beings, in population of humans, we cannot ignore the deaths by other causes like premature births due to malnutrition or inadequate medical supplies, or deaths by hurricanes. Well, hurricanes come in the natural deaths, but because of the violent crimes or accidents and epidemics. So all these things can happen, and we assume that the death rate is proportional to the interactions, the number of interactions between people, which is called like two-party interaction. Like when two people meet, what are the chances of transferring disease from one transfer of disease from one person to another person, a deadly disease. And so we consider the number of two-party interactions, which is p times p minus 1 over 2. So we say the death rate is proportional to this quantity, and so we get a new constant of integration here. Sorry, the new constant of proportionality here. We are calling it K3 because we have already used the K1 and K2 above. So I'm just following the book. So, so this ends up giving us a differential equation which looks like this. dp by dt is equal to minus a times p minus p1. Now what is p1 and what is a? Well, they are these quantities. Now what are these k1, k3? Well, remember k1 was the population, the growth rate of population constant, and k3 was the constant of the death rate over here. But usually these are not given, so we have to find a way to figure out what is A and what is P1 using the given information, and I will quickly go over that here. So we can do the same thing, over here we can move the P quantities on the left, and they come in the denominator under dp. So the left hand side becomes dp over p into p minus p1, and on the right hand side we are left with negative a dt. We integrate, but this will be, the left hand side will be integrated by using partial fractions. I have shown the work here. If you get a chance, look at it. If just for it will be a review, and we end up getting this. After integrating, the left hand side looks like this over here. So now we bring that quantity that we got by integrating, and then on the right hand side the integration is simple, which looks like this. And then by keeping our work, we have to get p by itself. So here is what we are getting, equation number 1, that is the that will give us the p, because one more step that moved this p1 over here. But remember, we still have to find the constant here, c2, and we use in our p of 0 is equal to p sub 0. We can get the c2, which is coming out to be, so negative c2 is equal to p1 minus p0 over p0, and plugging in here, simplifying, we end up getting equation 2, which is the logistic curve. Now you will not be asked to show all this work, but what you should know is the how to use this to find out our solutions. So the example I will do in the next video, and explain how to get the P1 and the A from given information.